Okay, hi everyone. My name's Chris, and today I'd like to talk to you about creating Debian-based embedded systems in the cloud using Debos. I'm an engineer at Collabora, and I work on custom Debian distros for cloud, embedded, and PC applications. I work on continuous integration of these distributions, packaging for these distributions, over-the-air upgrades, tooling, and I'm also learning some Rust as well. So today we're going to talk about why you want to use Debian as a base for your distribution over certain things like Buildroot or Yocto, some of the internal design decisions of Debos, and how to use Debos. Debos relies heavily on YAML configuration files. I've left a link here for a tutorial if you're not familiar, but it's very simple really. I'm also going to go through some future plans for Debos, and hopefully at the end, if we've got some time, I'll take some questions and post some answers. So first, we're going to talk about what is a GNU/Linux distribution. Basically, it's a collection of software packages or packages of software created for that distribution. It's also a collection of like-minded developers that work together onto the same goal. And each of these distributions has a different goal in mind. Some of them might be financial, others might be social. So Debian and Ubuntu use the package or apt, and the Debian goals are mainly social. Red Hat and Fedora uses RPM, Yum to install packages, and their goals mainly are financial. So they're looking for stable distribution for business, really, for enterprise customers. Everyone's got their own preferences. You pick and choose with what you like, really. In the end, the software you end up with is pretty much the same anyway, so it doesn't really matter that much. It just happens to be that my personal preference and a lot of Collabora employees' personal preference is Debian. So why would you want to create your own distro? So most hardware development kits these days are supplied with a general purpose distribution for your own evaluation. So these can have old kernels in, old packages, outdated configuration, insecure stuff, really. So normally you want to use a reference distribution to evaluate on the hardware, and then most of the time people are stuck with what to do after that, how they port their software to these platforms. You also may want to create cloud images, so for instance AWS, Google Cloud, DigitalOcean, and you want a nice stable base for all of these things. So you want to create your own distro rather than use something off the shelf and then have like a custom script install everything that you are going to want to use. Normally in these distributions that are supplied for evaluation and cloud images, there's a lot of bloat that isn't actually related to your final application. As I've already said, there's outdated and insecure packages and lots of incompatibilities, really. Obviously, there are applications where this isn't a problem, but I mean, on the whole, really, if you buy one of these cheap dev boards, really, you're going to get something that is outdated and unsecure, really. So it would be nice to create your own distro to put onto a board like that. But your own distro or your own flavour of GNU/Linux is a lot of work to maintain. I mean, there's a lot of packages you've got to create, a lot of work you've got to do to pull in security updates, pull in packages, like it's just a lot. So my suggestion is you don't need to reinvent the wheel. You want to base on a proven technology. So that brings me on to Yocto Buildroot, which is a proven technology used for embedded platforms. Excuse me. Now, I would say that using Yocto Buildroot is good, but only really for the sort of hardware like these cheap embedded boards from China, or your own custom hardware. Using Yocto Buildroot is quite difficult when you want to do something generic, like make a cloud image for AWS or make an image for laptops or something like that. Also, Yocto Buildroot create totally custom package, create a custom distribution, or rootfs in the case of Buildroot. It can become a bit of a maintenance nightmare, really, because you've got all of these packages, and if you deviate from the upstream at all, really, then you've just lost your security upgrade path. All of the packages are compiled on your machine, so basically, Yocto Buildroot, they download a compiler, source, compile the compiler, and then compile each of the packages. This can take many hours, and you really need some heavy hardware to be able to do a good job. There is a high learning curve to using these tools. I mean, it's not something that you can just make in and you end up with an image that works. You've really got to invest a lot of time and effort in creating the image and customizing it for your purpose and your target device. And really, my problem with Yocto Buildroot is, why make your life hard? I mean, things are out there already to make your life easy, so we all like an easy life, don't we? So Debian is traditionally seen as a desktop operating system, but in recent years, a lot of effort has gone into enabling embedded targets like the Raspberry Pi, for instance, and other cheap embedded boards. There's a lot of work that's gone into enabling Debian on RISC-V, as well as ARM, and this work continues. Debian was released in 1993, and it's quite widely used. I mean, it's in the DistroWatch top 10 list. I think it was number 3 a couple of years ago. It's dropped down now because of some Debian-based derivatives of push up high, like Ubuntu and elementary, things like that. But still, really, Debian does dominate. Debian and its derivatives do dominate the DistroWatch list. Thousands of volunteers shaped Debian into what it is today, and they all follow the Debian Free Software Guidelines and social contracts, which have also been shaped to make sure that Debian only contains things that are worthy of being included in a kind of decent operating system, I suppose. There are well over 50,000 official packages. Most of these are popular. There's also quite a few libraries. All of these are really easy to install. You can just do apt install and then, the name of the package, like Firefox or LibreOffice or whatever. And everything ships with a configuration that makes sense for most kind of uses. There are different ideas of what kernel to use. I mean, there's a herd kernel for Debian. There are different packages for things like desktop environments, and there are also packages for different web browsers. So, I mean, you can pick and choose basically what you like to make your system the way you want it. There's a really great community around Debian. There's lots of tutorials, there's forums, mailing lists that are fairly friendly. It's easy to get started. I mean, some of the things like bug reports are fairly archaic when you have to write an email, but all of these processes, because they've been around for so long, they are a nice process that everyone kind of understands how to do. So I would say that it's fairly easy to get started with Debian. So there are at least three branches of operating system for Debian. There's stable, testing, and unstable. Stable at the moment is currently known as Buster. Testing is known as Bullseye, and unstable is always known as SID. So stable and testing, the names of these change based on the release, but stable, testing, and unstable are kind of like symbolic links to these official names. So if you stay on the stable branch, you'll always update to the latest stable. So there are timely security updates in Debian. So basically, as things are improved upstream, they generally trickle down into Debian packages. I mean, there was this recent Bluetooth bug that was found fairly recently, and I think it's taken about less than a week or so for that to trickle down into Debian stable as a security update. The community are fairly good on that. There are also paid developers that work on the security and the vulnerability updates. So you can be assured that these will be trickled down really quickly as and when they're needed. Most importantly, using Debian as a base will allow you to work on the most important part of the project, which is your application. You haven't got to waste time worrying about what the underlying package is. You just pull from someone else who's done all the QA testing. It's quite a nice experience, really, in terms of developer time. I mean, I've heard of some developers spending half of their week worrying about security updates and the other half of their week working on the application. With using a distro as your base, such as Debian, you can really reduce that down to working on your application for probably 90+% of the time. So as we've already said, there are stable testing and unstable releases of Debian, or kind of branches, and each of these branches has a name. So Buster, Bullseye, and Sid, which are symbolic link, and there are symbolic links to the stable testing and unstable. All of the bleeding edge software is packaged into unstable. As soon as the package has been built for unstable, it's released into the wild, and then developers usually run the unstable release, and this makes unstable a QA staging area for the testing release, really, because packages trickle down from unstable into testing around 2 weeks after upload, only if no major bugs are reported. So the developers who are running unstable essentially do all the QA testing on the packages for about 2 weeks before they're pulled into the testing release. So really, testing is about 2 or so weeks, unless there are any critical bugs, behind unstable, which makes for quite a nice, fairly stable release. So stable release is frozen for about 2 years. After the release is frozen, only security updates and minor releases of packages are included in the release. So you don't get the latest and greatest software. You can enable the backports release, which brings some of the latest and greatest packages down that certain developers are interested in, such as the Linux kernel. I mean, in Debian stable, the Linux kernel is quite old. So if you're going to run stable, I'd suggest using backports to pull down the latest versions of packages. You wouldn't want to install or mix packages from different releases, because this can cause dependency nightmares with things like libraries. It's just generally not a very nice way to do things. I recommend using testing, unless you're very brave. I mean, I use SID. A lot of Debian developers use SID and don't really see many problems. But when you do get problems, it's kind of a big problem to sort out. So I would recommend testing for that extra bit of QA. Some people say that stable is quite old. I would disagree with these people and suggest that if you use stable along with backports, you can have a fairly up-to-date and modern system, which is very, very stable. Also, these days, most software is packaged using Docker or Flatpak. So if you really wanted the latest and greatest software, I'd suggest using Flatpak or Docker to install packages, really. So some disadvantages of using Debian. At the moment, Debian only caters for systemd. I mean, my view here is that systemd is the way to go in the future. Systemd is maturing really nicely these days, but Debian is changing now to let people try to choose their own way of starting the system. Which is quite nice. I mean, the thing with Debian is changes are seen quite they're quite conservative, so changes aren't necessarily implemented very quickly. They were very conservative of new technologies. Packages are built with glibc, so you kind of can't run Debian on a microcontroller, which I don't think these days you'd want to anyway. I think using systemd and glibc is quite a nice kind of combination for medium-sized boards. Originally, Debian was designed with desktop server use in mind, but these days there's been a lot of work on embedded platforms, and you can quite happily run Debian on a Raspberry Pi or any kind of ARM RISC-V board. It just really depends on the kernel bootloader, which are being packaged for Debian. So documentation in this area could be improved vastly, but I think that what there is out there now is fairly good. I mean, as I've said already, there is paid security support, but it's quite limited. I mean, you really are thinking about the select few that would actually want to pay for security support, but it is there. It's just not something that could really be relied on. Debian also has a quite slow release cycle. I mean, releases are basically done when they're ready, which averages out to about every 2 years. But this really isn't necessarily a bad thing, since SID contains lots of new releases, so things are nice there. So now you know how the background behind why you'd want to create a Debian image over something like Yocto or Buildroot, and now I'm actually going to go through how you would create your own custom Debian image, or Debian file system, root FS, whatever you want to call it. So the first step you'd want to do is create an image. You'd want to use something like DD here to allocate a file of, say, 4 gig, however big the image is you want to create, all of zeros. You'd want to use a tool like fdisk or parted to create a partition table on that image. That could be GPT, MS-DOS, whatever your hardware really requires. For x86 platforms, using things like EFI boot, you'd want to have a GPT partition, but some embedded boards are quite fussy on what they'll boot. Really, the first stage bootloaders are quite fussy. Then you want to format the partitions using the MKFS tools. Most cases you'll want to have a root file system for your root around sort of a gigabyte or maybe more. You'd want any other partitions which are required for the embedded platform that you're running on. So for instance, EFI would need an ESP. Platforms like Rockchip, they need kind of GPT partitions for U-boot and separate partition for kernel to live in. All of that is really implementation detail of your particular system. After that, you'd want to mount the partitions in a loop device using something like kpartx, which is always really a problem. I mean, sometimes loop devices just fail for no reason on certain machines. It's not really that reproducible. After that, you can change root into that mounted image, and you can use debootstrap to create a basic Debian file system. Debootstrap basically downloads the Debian packages which are required for a very, very minimal system and installs them, and then eventually you end up with a system that's got some basic tools in it, like a shell, kind of systemd. You've got apt in there as well, so then you can expand your system after that using tools like apt to install other packages. You can install custom packages using dpackage. After that, you're going to want to set the host name of the system, add user accounts, other configuration, things like that. And then after that, you want to do the cleanup stage where you unmount the image and clean up all the loop devices. And then you're going to want to do something like compress the image to a bmap file if you're going to be flashing to an eMMC, for instance. You want to save the build logs so that people can see what's happened in a reproducible way. And this is nice, it works. There are some tools out there that do these steps like this. For instance, Spindle, which is for Raspberry Pi. And it works until it breaks, really is the problem. And we've had this with loop devices. I mean, they're so fragile. I mean, one kernel version it will work, the next it won't. There are also issues with loop devices where if you're building lots of images in succession, eventually the whole kernel will lock up. This is just a problem with using loop devices. There's no real fix for it. So there are lots of tools out there that do this, as I've already mentioned, this Spindle. I've linked here a presentation called The Many Methods to Build a Debian Image, which include lots of tools and how to kind of use these tools to create Debian images. Interestingly, Debos isn't on the list yet. I'll have to get in touch with Riku to try and introduce him to Debos, or maybe if you're watching this presentation now, that would be also quite nice. But basically, the conclusion of this presentation is these other tools serve very specific purposes. They're not quite generic enough. So Debos was designed to be inherently more flexible than these tools, and also robust against the random failures like issues with K-part X and loop devices. Excuse me. So Debos generates a complete distro from one configuration file, and that configuration file can be stored in version control, which again is quite a nice thing. Changes in versions of Debos don't really matter so much because Debos only handles kind of generic things, as we'll come on to in a minute. Other tools, the version of the tool that you use to create the distro can have an effect, because some of these tools have certain features which are enabled later down the line. So Debos is constantly being improved upon by Collabora, and the main reason that Debos was created was for the Apertis automotive Debian derivative, where the developers were having such problems creating these images using these steps I've defined already with loop devices. They just thought, right, we need to create a complete custom bit of software to do this. So I also think that getting started with Debos is actually very quick compared to some of these other tools. These other tools have got their own quirks, intricacies, and things to learn. Obviously Debos does as well, but it's a lot nicer learning Debos than some of these other tools. So Debos runs a VM on your machine using a library called Fake Machine. Currently we use KVM, a kernel virtual machine, to create this virtual machine. But as we'll come on to later, we are improving this. So the disks are attached to the VM itself, so there are no loop devices involved, and attaching disks to a VM is very, very commonplace. I mean, every VM's got a disk attached to it, so this works very nicely. Excuse me. Under Debos, the steps to create your image are contained in a recipe file, and this recipe is translated into commands which are ran inside the virtual machine. And these recipes and the commands are known as actions, which abstract the changes to the files and the commands that are ran in quite a nice way. If there's no action already available, I'm going to go into what actions are available in a second. If there are no actions, you can basically just run a shell command or a script inside the VM. It's quite easy to do that. We also welcome action ideas as well as action patches upstream. And when things go wrong, it's really easy to clean things up. All you do is you kill the VM and everything's gone away. You can restart from how you were and it works very nicely. So the images are reproducible on your PC as well as the cloud. So basically anywhere you run the tool, you'll end up with the same kind of output. So there are loads of people using Debos. Apertis, as we've mentioned, is a Debian-based platform for automotive and consumer use, and it uses Debos to generate reference images for lots of different platforms. They do cloud images, they do images for Raspberry Pi 3 and 4, they do lots of strange reference platforms for IMX6. The list really is endless. Kernel CI, which is a Linux Foundation project, uses Debos to generate the root file systems for continuous integration of the kernel. And it also uses Debos to create root file systems for Lava health checks, which is used under the hood of kernel CI. Redaxa, I hope I'm pronouncing that right, they use Debos to generate reference images for one of their boards. called the Rock Pro PX30. Hopefully we're going to see them use DebOS more. We've been working quite closely with them to introduce their developers to DebOS, really, since they were using one of the build scripts I was talking about before, where things just go wrong quite a lot of the time. The Mobium project, which is Debian for mobiles, is a project by one of my colleagues, Arnold Ferraris, that uses DebOS to generate images for PinePhone, PineTab, and the Libre M5 phones. And I've heard there's quite a lot of interest in Mobium recently, so that's definitely a project to check out. Plasma Mobile, my KDE project, they use DebOS to generate reference images for their Neon platform. Gemian, I hope I'm pronouncing that again right, is Debian for a PDA Cosmo communicator. They use DebOS to generate images. And reproducible builds use DebOS to make sure Debian packages can be independently verified by using, by creating images really for base images for the reference build system. There are plenty of people using DebOS. If I've not included you on the list and you're upset about that, please email me and I'll add you to the list for the next time I make this presentation. So that brings me on now to what actually is DebOS. So the core of DebOS is written in Golang. And there's no need to know Go, only if you want to write patches upstream to us, which again would be very kind of appreciated. The reason Go was chosen is because it's similar enough to C, and there's a low barrier of entry. I mean, you can learn enough Go to start writing patches probably in an evening. My biggest problem was working out how to compile everything and where all the source was kept, but we've got documentation on how to do that now. There's a separate library called Fake Machine, which handles the virtual machine, and that abstracts all the virtual machine stuff into a separate place. So DebOS is kind of runs on top of that. DebOS and Fake Machine are in Debian stable testing and SID, so you can download those for your AMD 64 host and run them on your Debian system. There's a Docker container for DebOS, which you can run on any kind of Linux-based system, as long as you've got KVM available and you're in the right group. Or finally, you can install DebOS from source on other operating systems like Arch. There are certain intricacies and things to be careful of. For instance, on Ubuntu, your kernel image is read-only by root, so you can't read the kernel. You can't read the kernel as a regular user, which basically means you can't bring the kernel up inside the VM, which is basically a non-starter. So I would recommend for these platforms using a Docker image, because the Docker image contains kind of everything needed. It contains the kernel binaries, all of the libraries, and they're all kind of tested together. So you can run whatever kernel version you like on your system. So long as you've got KVM available, you can run DebOS through the Docker container. So I've kind of alluded to this already, but DebOS recipe is a YAML file which basically defines the steps the software needs to go to create the image. YAML is fairly simple and can be version controlled in the same way as any other script, really. So just a Git repository is what I'd recommend. And as we'll see later, that can also help for things like continuous integration. The recipe consists of a header, which has got the metadata. Currently, this only consists of the architecture you want to build for. And then after that, there are multiple actions which are chained together. Each of these actions has their own properties. Again, I'm going to come onto these actions in a minute and what they all are and how they all work. Comments can be put in the file. They're prefixed with the £sign if you're American, or hash if you're English. The YAML file is pre-processed through a templating engine, so variables can be passed from the command line, and there's also some basic scripting in there, so if-else statements can be used. And together with variables, this is quite powerful. You can basically choose different packages to install based on for instance, what architecture you're building for, or you could have different variants of your image which have got different packages. The list really is endless. Also, the other nice thing is recipes can include other recipes, so you can abstract things off into their own separate files. So here I've got an example. If you want to follow along at home, you can copy this down as simple-ospack.yml. You can see the description here includes the fact that this recipe will create a table of a basic Debian system. So the architecture is the first thing that's defined, which is AMD64. This could easily be ARM, HF, ARM64, RISC-V, PowerPC, any basically Debian supports architecture. And then after this, we've got a list of actions. You see, there's the action stanza, and there are actions stored in an array here. Each has a prefix, the little dash, and then actions. There are 4 actions here. One's run after the other. So basically, we run debootstrap to set up the basic system. We then run apt to install a package, and then we run a command to set the host name. And then we pack everything up into a tarball, basically. And if you're following along at home, you can basically install Docker from your system, and then you can run the Docker image and run the YAML file I've just spoken about. And basically at the end, you see this output, and you get a file called simple-ospack tarball. So I've had to remove some of the output here because otherwise it won't fit on the screen, but basically you get all of the standard out and standard error of any command that's ran in your shell, which makes it quite nice because you can just, if there are any issues, you can just see on the screen what's happened. You can see exactly what's being installed, what steps were taken. So basically here again, I've just shown the recipe on the left-hand side and the output on the right, and how each action is shown on the right-hand side. And the image basically takes about 4 minutes to create, which is not that long. I mean, it gets a little bit longer when more things are done, but I think you can have an image in probably about 20 minutes, really, a fully featured image, which is quite nice. You can also run Debos under GitLab. We use GitLab CI at Collabora to create images for clients. And you can basically set up GitLab CI using YAML again. And here is a very simple GitLab CI file, which runs the same example before. And I think here we've got less than 20 lines, and every push to that repository is built using this continuous integration pipeline. You can set up schedules and kind of all sorts. It's quite a nice system, really. But I've also included a screenshot here of basically what you see. There is a little tick at the bottom for each of the stages which are ran. You can see it's ran for 10 minutes, what commit that relates to. And also, if you get failures, GitLab will very kindly email you, which is quite nice. You can also see the output of the commands which are run. This is stored so everyone who's been given permission can see it. Next, I'm going to come on to the actions that are available for you. The first and most important action really is debootstrap, which sets a basic Debian system in the target. You can choose where the packages come from, whether they come from Debian, Ubuntu, any Debian derivative really. You can choose the suite, which we've already spoken about earlier, so that could be stable, unstable, SID, or any of the Ubuntu suites, whatever. You can choose the components which go into that, so you've got main, contrib, and non-free for Debian, but you can choose whatever component you like. Also, you have the variant parameter. If you do not include this, you'll basically get a full Debian system with lots of small packages, but we tend to use min-base because that really is the minimum system that you would have, which just has the essential packages and apps, so you can install more packages, basically. Then you have the apt action where you can install more packages and the dependencies. It just calls apt and handles the dependencies the same way as if you're calling apt on your system. Then you have pack and unpack actions, which pack compresses the complete target file system to a tarball. Unpack uncompresses the file system tarball into your target. So we use these actions so you can create an OS pack, which is used in multiple recipes. So you can have one OS pack, which is included in 3 different image recipes, for instance. And at the moment, gzip tarballs are the only supported compression type. Which then brings me on to the image partition action, which allows you to actually create an image. There are lots of parameters here, as you can see, but basically it creates an image and the partition table inside that image and formats all of the file systems. There are lots of different types to choose from. There's the standard X234, FAT32. We've also got some interesting ones like ButterFS, F2FS. We also welcome patches or ideas here if you want to add more file systems. We also support the none file system type, so you could basically then just write your own stuff to that partition, no file systems formatted there. This image is then attached to the VM, and then if you've set up the mount points, the mount points are then mounted inside the VM. And also from this, later on an FS tab file can be generated from this list of mount points, which is quite nice. You can only use the image partition action once per recipe, and it just calls standard tools like parted, mkfs, fdisk under the hood to do the creation of the image. So we've got the filesystem-deploy action, which is usually used after the image partition action, which basically copies the whole file system onto the image. Usually by default, the root file system isn't stored on an image, it's stored in a tempfs, usually 2 gig by default. And then we use a tempfs because it's a lot quicker than writing to disks in some cases. So usually you want to do all of your customization to the image or the file system in the tempfs, and then right at the end deploy everything to the image, just because writing to disk is usually a lot slower than writing to memory. After you ran the file system deploy action, everything is executed on the image basically after that. There are also some helper functions here: set up kernel command line and append kernel command line, and setting up the FS tab, which basically creates the FS tab file from the image partition action. And it uses the block UUID for this, which is fairly primitive. I mean, in some cases you want to use the block label rather than the block UUID, but you can always overwrite the FS tab yourself. And in these cases, we let you set your own FS tab up. Also, you can create the kernel command line file, which basically is the parameters which are passed to the bootloader for setting up scripts. Basically, it's implementation detail. So if you ever use Docker, you'll know what the overlay function does, but the overlay action basically copies files recursively from your host system into the target file system. The source directory is relative to the recipe file, so you can include files from the same directory as your recipe file into the image. This is useful for including things like configuration files or little bits of scripts or something that you want to include in the image. The permissions are preserved as well, so this is a really handy function to just copy stuff into the image, really. We've got the raw action next, and the raw action basically writes an image to the partition or the image itself. This is used for installing bootloaders to the image or copying pre-prepared images to a partition, basically. And under the hood just does something like dd to install the image into the partition. We've got the run action. The run action basically allows scripts or commands to be run inside the virtual machine. You can run these on the fake machine itself or inside the target root file system, or they could be run after the virtual machine has been shut down. Your scripts must be executable and they're stored relative to the recipe, which again is quite nice because you can store the scripts under version control as well as the YAML recipe, so everything's all in one place. You haven't got to dig around in lots of different places to create your OS image. If the command fails, then basically Debos will fail as well with the standard out and standard error of the command that's ran. So this is quite nice because if any failures do occur, they just get trapped. And if you pair this with something like GitLab CI, you can easily get a ping over email when something fails, and then you can just go in and fix it at your leisure, really. Excuse me. So basically, commands and scripts are mutually exclusive, so you can only run a command or a script. So this brings me on to the more complicated side of things now, like variables and scripting. So in this example here, we have 3 variables which are passed in from the command line: the architecture, the suite, and the image name. And we also have some defaults. So this is basically just a quick way of showing you how the variables are used. In our third variable, the image, we basically use the suite and the architecture to pre-prepare the file name of the image, which is using printf, which is quite nice. And these defaults can be overwritten from the command line using the -t or template variable. And you can see at the bottom there's a couple of examples of how to use the architecture and suite to change these variables from the command line. Okay, so then we've also got if-else statements. So you can see at the top we've defined architecture as a variable with a default of ARM64, and we could pass that in through a template variable, and the example uses if-else to check if the architecture is equal to a certain architecture, and it will install certain packages depending on what architecture you've chosen. This is the sort of simple scripting you can do. It may seem simple, but it's very, very, very effective. So you could have variants of different image types, for instance, a minimal image or a maximum image, which has got lots of different packages in, say, for development. And then for your actual release, you would have different packages in. Or for your debug release, you would install an SSH server. And for your production release, you wouldn't install the SSH server. Things like that are very easy to set up using these if-else statements. This also brings me to the recipe action, which allows you to include recipes inside other recipes, which is quite powerful because it allows you to abstract things elsewhere. So you can also pass variables in here. So for instance, you could use this for components. So you can have a recipe component that installs LibreOffice, as well as setting up all the configuration files there. Or you could have a recipe that installs the debug version of your stuff or application, and then just hides all the implementation detail of that in a separate file, which is quite nice. So some more examples, more fully featured examples. There's a basic Raspberry Pi 3 or 4 image, which is a good starting point. It's basically one file and some scripts which create an image for your Raspberry Pi. Most people have got Raspberry Pis, so if you're interested in making a Raspberry Pi image that's completely custom, I would look here to this example. Apertis, these examples are not for the faint of heart. I mean, these are quite in-depth. They create lots of different images for Raspberry Pis. They create images for other platforms as well, all from a common base. And there's a lot of scripting if-else statements in there. So I'd recommend checking that out if you're interested in some quite heavy-going examples, really. Other than that, there are the examples which I linked to earlier in the presentation about who's using Debos. So check out there. So the future plans we've got for Debos include improving the documentation, adding some example recipe files to hopefully get more people using the tool. At the moment, it's really been a lot of internal use, and not many people outside of the company have really heard of Debos, so really we want to create some more recipes and get more people using it, really. So that's the biggest goal we've got, really. By the end of this year, we want to add in automated testing to make sure that each push to the repository that we make or any new patches that we get don't break any old sort of functionality. We're going to do this by adding in some self-testing recipes that is ran sort of on a scheduled run as well as on every push to the repository. We want to add in user mode Linux support, and this kind of goes back to the original point that we made about Debos only running with KVM. So our GitLab runners have been designed so that KVM is installed on them, but normally if you run GitHub Actions or GitLab runners, they don't have access to KVM. So we want to add in UML support here. User mode Linux is a bit slower than KVM, but it works quite nicely for GitHub Actions and GitLab self-hosted runners. This kind of is a game changer because we can then build images on GitHub. The example images or the example recipes that we've created can be installed and tested by anyone just by clicking the download button, and then people can build their own images on GitHub as well. So that would be a game changer in my opinion. We want to add in some more useful actions. So at the moment there's no real official way to install a Debian package from a file. We want to add in that and some other useful actions. Again, the actions that we've got are fairly generic and should work in a lot of cases. If you spot an action that you think would be quite useful, please feel free to open an issue on GitHub and we'll talk about it there. Next year, we'd like to add some support for Arch Linux and other distributions. So that's basically running Debos on Arch as well as potentially creating Arch Linux images. There's a lot of interest inside Collabora for creating images for other operating systems in the same way that we do for Debian. And again, more examples and documentation. I think after that's all in place, we're ready to release version 1.1. And after that, I think we want to fix all the bugs, because I'm sure there are some. We run Debos kind of at least a few times a night with the Pertis, and we're picking up bugs as and when they come, but everyone always has their own way of doing things, so we're always open to fixing bug reports and discussing them on our issues list. So please open an issue on GitHub if you do find anything. So then with that, I would like to say thank you for attending, and I'd like to take any questions. Collabora are also hiring. There's a link on the screen now. So it's a shame that we didn't get to meet in Dublin this year. Dublin is one of my favourite cities. This t-shirt I'm wearing here is actually the skyline of Dublin. So really with that, I hope you and all of your family are staying healthy and safe. And thank you again for listening.